When the computer starts up, after the BIOS has run all the hardware checks and initializations, it will boot the computer by reading in the first 512 bytes from the disk into the memory location 7C00. Boot sector consists of three different things. First, we have 440 bytes of code, our bootloader. Then we have the partition table, which consists of 4 entries, one for each partition, 16 bytes each. Finally, we have 2 bytes with the signature 0xAA55. And that is so the BIOS will know that this is a valid boot sector. So our bootloader will need to go through each partition and check the bootable flag if it's true. When it finds a partition with the bootable flag, then it will check the CHS start field. That is the coordinates, so to speak, the hardware location on the hard disk drive where we find the operating system. And our job is to copy the first 512 bytes from that location to the memory location 7C00. And then we can boot the operating system. So let's get started.
So guys, welcome to today's show. So today we're going to create our own bootloader to load Linux. And I'm going to call it Lux bootloader. And that's short for Linux bootloader. So let's first take a quick look at how a bootloader is organized. It's 512 bytes and the first 440 is the actual code that runs. Then we have 6 bytes of optional values, which are usually not used, or it's not necessary to use them. If we can't fit our code inside of here, it's possible to use these 6 bytes for code as well. And then we have the partition table. So we have 16 bytes for each partition, up to 4. And then we have 2 bytes at the end with the signature 55AA, which tells the BIOS that this is a valid bootloader. All right, so how does this partition table look? It contains different kinds of stuff. The important stuff is this first one, the drive attributes. And the most significant bit, if that is set, that means that this partition is bootable. So we need to check and find the first bootable partition and use that one to boot the system. And then we have the CHS address, which is the location physically on the hard disk drive where the boot code is located. So we need to read in this stuff from the hard disk drive and let it load the operating system. Then we have some other stuff here which isn't really necessary in our case. All right, and we need to perform 3 different operations. First, when the boot loader is initialized, the BIOS has copied it to the location 7C00 inside of RAM, all the way through to 7EFF. That's 512 bytes. So what we need to do is we need to locate the bootable partition and use this CHS address to read in from the hard disk drive 512 bytes of the boot code starting at the position here. And we need to copy it to the same location, 7C00, and then let it boot the system. So you might notice that we have a problem here. We are located at this address, and this code needs to be at that address. So it's a conflict. So the first thing we need to do when we start our bootloader is to copy ourselves somewhere else. And that's called a relocating. So we can copy it basically anywhere inside of the RAM. I'm gonna copy it to 7800, so we have plenty of room. Because I want to use this address as the base of the stack as well, and I don't want it to conflict with each other. So this is a good enough way. So we need to copy the entire bootloader, including everything, into this location and then reload it. So we start from the beginning, but at this address. When we execute the code the second time, we need to know that it's the second time so we don't start copying ourselves all over again. And then we can start reading from the hard disk drive, copying this stuff to this location and let it boot the system. So that's basically it. And this gives us some trouble because if we make our code use this as the base address for locating variables, for instance, it will only work the first time we run the code. Then the base address will change and our code will remain the same, which is a problem in some cases. So we need to take that into account also. But we'll cross that bridge when we get there. So let's start by setting up a project. I'm going to create a folder called looks, and I will go into it and set it to my home. And I'm coding this on my Linux server remotely. And I'm going to launch a VS Code remotely through the Sociopath SCP client, so I can edit the files remotely. So I'll take this looks directory, right click and open in editor. So each time I save a file, or create a directory, it will automatically update on the server. Okay, so let's see how we're going to structure this. I want to have a main assembly file, which I'm going to call looks.asm. And all bootloaders needs to be coded in 16 bits assembly, because the computer always starts up in 16-bit mode for compatibility. Right. So let's also create a makefile so we can compile this thing. So let's see. We want to create maybe we should start with some flags. So we're going to have some kind of flags and some kind of linker flags. I also want to create an include directory where I can have some include files. I need to choose new folder. So let's call this include. And in order to set the include path, so we just can say include file.h, for instance, without specifying path and so on, we need to set an environment variable, which is called env. And we want to set the -i for include, and we want to provide the include directory like this. And we need to export this environment variable so it will be part of the rest of the file. So let's see. So we want to create a lux.o file out of lux.asm, and in order to assemble this, we run nasm with some possible flags. And we provide the input file like this. When we have that, we want to create the binary. So first, I want to create an elf file. It's not necessary to take that step, but if we want to include other stuff, it makes stuff easier. So I want to create a lux.elf out of lux.o. And I'm going to use a linker with some possible LD flags. And we want to take the input file and create an output file. Something like this. And when we have the elf file, we can create the final binary, which I'm going to call boot.img as an image file. And this requires lux.elf. And I'm going to use obj copy, which is a command that transforms between different executable formats. By the way, I want to remove the executable flag on this elf file. So I want to copy the source file to the output file like this. Or no, not to the output file. Let's take an intermediate step. So let's say we have a lux.bin. And I want to make sure it's 512 bytes or a multiple thereof. So I'm going to use the truncate command and say that this should be a multiple of 512 bytes. So we fill it out with zeros if it's not the correct size. And to the obj copy command, we need to supply the source and destination formats. So let's check the help file for this. Obj copy -help. I think it's I and O. Yes. I for the input format and O for the output format. So we can do obj dump -help to see the different formats. And I'm going to make it a 32-bit elf binary. So this will be the input format for lux.elf. And the output format will just be a flat binary. So machine code instructions only. All right, I think this is okay. And then I need to do some other stuff, but I think we can wait a little bit with that. So let's just rename this looks.bin to the output format boot.img. Something like this. And I want to have a clean directive which will delete all O files, all image files, all ELF files. Yeah. And since this clean directive doesn't produce any output, we need to declare it as phony. And finally we'll have the all, which will just create boot.img. Alright, I think this is correct. Let's put in some stuff here just to test it out. Well, we can just do something like this. And let's see if it compiles. Okay. We need to specify the output file for the NASM command as well. Like so. File not recognized. Maybe we need to add the flags and say that, just let's see, NASM-F ELF, I think. And it complains that we didn't export the start label. Global start. Now I believe it should work. Yes, no errors. And we have this boot.img, which is 512 bits. And I have created an alias objdump86, which you can copy. It runs the objdump, which is a disassembler that takes a binary executable and shows all the binary machine instructions. And I have configured it to run as i8086, which is the 16-bit platform. So I can just run objdump86 boot.img and I get the disassembly here. By the way, I don't want it to be green, so let's see, let's do similar with this file. Alright, so now we have the basic setup, but we need to define how the image file should be organized, because there are three different parts. We have the code part, and this I will skip for now, so we will just leave it as 0. But we have the boot code part. We have the partition table, and I will just add some dummy stuff here for the time being. Then when we run this for real, we need to copy this from the primary hard disk drive. So we have the current partition table. And then we need to have this 2-byte signature at the end. So the easiest way to organize this, I think, is to create an LD script file. So I'm going to call this looks.ld, and I'm going to choose not a plain text but a linker map file. So okay, so we need to define three different things. First, we need to tell it what the output binary format should be. So we can take that from here. So the output format should be this. And then we need to define the different memory areas. So the first thing is our bootloader. We need to define some flags for that, and this is going to be read-only, executable, allocated, and initialized. So basically this means that we are going to use this, and we are going to fill it with zeros if we don't use up all the space. Okay, so first we need to define the origin. And the origin is where this code will be in memory. So it's going to be 7C00. And then we have the size, I believe. So we need to go all the way down to this. Like so. And then we have the partition table, P table, and this is going to be read AI. The origin is going to be, we start here. So we need to take this origin and plus 1 BE. So basically it's going to be 7 D BE. Since this is 7C, this would be 7D. And the size of this is 16 times 4. So that's 64, by the way. So I have some alias for converting between hex and decimal. So 0x40 is 64 bytes. And this hex is just a printf that turns it into hex. And I also have a dec alias to turn it back into decimal form. Right, so the size of this is 0x40. And finally the last part, which is the signature. The origin of this is 0x1FE. So 7D FE. And the size of this is just 2 bytes. So this is the memory layout. And then we're going to have the sections as well. And the sections is this. Usually when we code something like this, we do section.text, for instance, and there we put all the code. So we need to take all these sections and map them to these memory locations. So let's begin with the bootloader. And the bootloader should contain all files that contains the bootloader sections. And this should be part of the bootloader memory location. And then we take the partition table and do the same. All files and the partition table. And finally, the signature. I don't think we should have yeah, we should actually. Then we have the signature, and we do the same here. And that's basically it. Now we need to add this file to the makefile LD flags. And I don't remember how to specify a script file, so I'll do this. -T. Something like this, and we need to create those different sections inside of our code. So first we will have the actual bootloader, then we will have the partition table, then we will have the signature. And the signature will just be this here. So I'm going to, let's see, let's say we create a label, signature, and we define a word 0xAA55. So here it's in the opposite direction, but here we specified byte by byte. When we specify it as a 16-bit integer like this, we need to flip those. And the partition table, for now I will just do something like this and say that this is we will have 64 zeros for now. And the bootloader, let's just have our start label and our nope. All right, let's see if this compiles. Syntax error, line number 6. Okay, let's go to the man page. It's always difficult to remember all this stuff. So LD scripts. Name, origin, length, okay. So let's do like this. And let's try this again. Memory region bootloader not declared. I forgot. We need to assign this to the memory region like this. And like this. Bootloader not declared. Oh, bootloader. Sign will not fit in region P table. P table length is this. Section P table, 64 zeros. And then we define a word. Length 2 FE FF. P8. 0D BE 0D FE. What does it say exactly? The section dot sign will not fit in region P table. But we're trying to put it inside of the sign, right? Section sign. Bootloader, P table, sign. Origin, length. What am I missing here? We have the bootloader, we have the P table, we have the sign, bootloader to bootloader, P table, sign. Oh, I have a dot here. small errors is hard to find sometimes, or locate. Okay, now it looks better. So now we have this file, and if we do an obj dump, we should see that we have the no-op at the first position, and then we have a lot of zeros all the way to the signature at the end. Okay, that's good. But in order to see that it actually is the correct format, we need to define this p-table a little better. So I'm going to create a structure which has this format, so it will be organized and easy to see. So let's create inside of the include directory. I will create a looks.h, and I'm going to define that this is an NASM file. And the structure format for assembly is a little bit difficult to remember, so I'm going to check the manual. So NASM struct. No, not this. Let's copy this and use as a reference. So I want to create a struct, which I'm going to call partition. And let's see what we're going to have inside of that. First, we need these attributes. So attributes, or maybe just like this. And we want to reserve bytes, 1 byte. Then we have 3 bytes of the starting position, so let's call this start. Res byte 3. Then we have 1 byte of type. Then we have 3 bytes of the last sector. And then we have the LBA. The LBA is a different format that uses a linear scale instead of the CHS format. We are not going to use this though, but let's add it anyway. So this is going to be the LBA, and this is 1 D word, which is 4 bytes. And finally another D word for the number of sectors. So number of sectors is another D word. And struct. Okay. So now we have defined the actual format of this. By the way, this is not 32, this should be 16. So inside our main file, what we're going to do is we want to include our looks.h, and inside of this partition table we want to create 4 different structure instances, and in order to create an instance we use this istruct directive. So let's paste it in here. So we're going to have our first partition, which is an istruct partition. That's the one we defined. And since we are only going to fill this with bogus values, we don't have to go through every different part of it here. I will just say at partition we want to reserve, let's see, let's do it like this. Let's do 64 bytes where we have the numeric value 1. End. So let's create 4 of these. This will be the second, and let's fill this with 2's so we can find it easily. And we do the third. And we do the fourth. So something like this. Maybe we can make it a little bit tighter. All right, let's see if it works. Times value minus 48 is negative. What? Maybe we cannot use times inside of a struct. Let's instead define, we can define a couple of D words. So each should be 16, by the way, not 64. Maybe that's the problem. 64 is the total amount. It should be 16 per structure. Okay. Still looks right. And let's do an object dump. So inside of our bootloader, we still have the no-op, and then starting at 1 BD. So let's look at this. 1 BD. Okay, I think it's the correct. Probably we have a lot of zeros here, and this starts with a 0. So, yeah, so this 0 is not part of this actually. It's part of the rest here. So we should start at 0, 1, at 1BE. 1BE. Okay, that looks right. And it goes all the way down here, and at the last byte we have the 55 and the AA. We don't, this to the right here is just bogus because it's trying to interpret this as machine instructions, but this is just data. So what we can do is a hex dump of this boot file, and here we can see if we go to 1B0, this is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. So it looks right. Okay, so now we're done with the partition table, we are done with the signature, and now we just need to code our bootloader. So let's see. I want to have some function which writes to the screen. It will make debugging a little bit easier. So let's start there. So let's say we have a main label where we want to start up. So inside of the start, we jump to main, the first thing we do. Then we can put our other functions on top here. So I want to have a function which takes a string and writes it to the screen. So let's say let's call this print. And first we want to initialize our stack frame as usual. So we want to push BP and move into BP our SP, as we usually do. Then we want to take the argument, which I'm going to place on the stack. So let's say we put it inside of our SI. And this is going to be BP. Usually in a 32-bit environment, it's EBP plus 8 to get to the first parameter. And if we run 64-bit, we have RBP plus 16 to get to the first. But when we run 16-bit like we do now, it's going to be the regular BP and just plus 4. That's the first argument. So we put that inside of SI. And then we're going to have a loop where we load one byte. So what this does is it takes the current position of SI, which in this case points to our string. It loads this byte, into the AL register, and it increases this by 1. So now inside of AL we have the byte. So we want to check if this is a null terminator. So what we could do is we compare it to, so we compare byte AI to 0. But this is not the most optimal way, or the most optimized way. When we want to compare something to 0, it's actually better to just do an OR operation on AI with itself. If this returns 0, we know that it is 0. So in that case, we can jump to some end. Otherwise, we want to print this to the screen. So we need to use a BIOS interrupt for that. So let's search for BIOS int 10H. And I like this Stanislav page. I'm gonna link to this in the description. I'm also going to link to this page about structs and this page about the memory locations inside of the LD script file. And of course this OSDev wiki where we have the rest of the information. Alright, so what we are interested in is I think it's this one, right? Right character at current cursor position. Let me just double check. Right text. Oh no, I think it's this one actually. Write text in teletype mode. Teletype mode basically means write to the console, one character at a time. So AH should be 0E, AL should have the ASCII character, and that we have already put there, right? Page number we can have 0, and the foreground we don't need to care too much about. So we can just initialize our, let's see. Let's initialize our BX to 0. So let's do an XOR, which makes it 0, and we can do the same with AX actually. So then we load that byte, or maybe not. BX we can 0 like this, but AX I wanna put this stuff here. So this should be the higher byte. So it should be 0E, and then we can have 00 here. And when we load, it will replace those zeros here. So at this point, we have all these different things correctly. So now we just need to do the interrupt. So we do int 0x10. And then we jump up to the loop, printing the next character. And when we encounter a 0 byte, we jump to this end label, at which point we can just move into SPBP. We pop back the BP. We can also take care of this argument here, or this parameter. it's a good way to do this. So we minus the SP with 4. So we no, not with 4, 2. The addresses are 2 bytes in 16-bit mode. So then we have removed this argument from the stack, and then we can return. So something like this. And before we even call any of these functions, we should initialize a few things. Let's move into AX the value of CS, which is the segment register for code. So we take whatever is inside of that and we copy that into a few registers. So we copy it into SS, copy it into DS, and we copy it into, let's see, CS, SS, DS, and ES. Let's also initialize the stack. So I want to have the stack at the beginning of the code here. So let's say we have a label on top, which is our stack. We can move into AX, that stack position. And then we can decrement it by 2. Minus it by 2, just in case, so we have room. And then we move into SP, the AX. So then we have initialized the stack. Alright, let's also say that we have some label which we can test this print function on. So let's say we have a string. Hello world. And we need to have a new line like this. And let's end it. Can we do this? I don't think so, actually. But we can say 0xa and 0xd, which is the Windows style new line, which the BIOS uses. And then we add it by a 0 byte like this. And how do we use this thing? Well, we move into some register our string. We push that string. We call our print function. And after that, let's jump to some halt label where we have an endless loop. So this is our halt. We want to use the halt instruction, and if some interrupt or something messes with that, we can have a loop here as well, which has a no up, and then it jumps to the loop, something like this. And by the way, we don't want any interrupt to mess when we do this stuff. So let's clear the interrupts and then restore the interrupts. Okay, I think this is going to work. Comma colon decorator blah 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 11. Okay, let's do this instead. this should be AL. Okay, let's do an obj dump. So here's our code. And how do we test this? Well, when this bootloader is finished, I'm going to create a proper Linux server and install this bootloader onto it. But during development, we need to make it a little bit simpler. So let's use the QEMU. QEMU. And I'm going to use the I guess system i386. And let's do like this because I want to find, there is some no graphic. Yeah, no graphic. So let's go to our make file and create another phony thing, which will be the run directive. And run requires boot.img. So we want to run QEMU in no graphics mode, which means that it will output all the stuff to the console instead, which is very nifty. And we want to create a primary hard disk drive based out of our boot.img. Maybe we can even do this. And then we need to specify the size of the memory. I think it's -s. No, it's not. Let's see. Grep memory. Size of guest memory. Here, configure guest RAM -m. So this, I believe, should work. Let's try it out. And if you don't have QEMU installed, you can do, let's see. You need to install the package QEMU system, or rather QEMU system x86. Then you should get all necessary things, I think. All right, and then we can just do make run. And maybe we can spell it better. No graphics. No graphic singularis. Hello world. Works perfectly. All right, so now we need to exit this virtualizer. So what we do is Control A, X. So you do Control A, you release, and you press X. That's how you exit QEMU. All right, so we have gotten a bit on our way. Now we have everything set up in the project, and we can start coding the actual bootloader, where the first step is the relocation, where we want to copy ourselves to a different memory location and restart everything. And this we'll do just after this. Sup guys, welcome back. So before the break we were able to print a message to the screen, and the next step is to take care of the relocation. So we need to copy the entire boot sector into another memory location. We need to launch our code once again from that location, and then we need to take care of the booting from the partition. So let's begin by creating some messages so we know a little bit about what's going on. So let's say, let's create message 1. And this is going to be relocating. And let's create a second message so we know when the relocation has happened. Let's do and these are just temporary messages during development, so we know if the things work or not. So relocation successful, something like this. And let's add the new lines and the character line feed and null terminator. So something like this. Right, so first of all we need to have a way of knowing if we are running the code the first time or the second time, because we will only relocate our own code the first time. And the easiest way, I think, is to use the DL register. Because the BIOS will put 0x80 inside of the DL if we are booting from the primary hard disk drive. And it will put, I think, 0 or 1 or something if we are booting from a diskette drive, which we most definitely won't. So we will only support booting from the primary hard disk drive. We will support different partitions, but only one physical drive. So when we launch our code the first time, DL is going to be 0x80. So we can basically check for that and then change it to something else like 90, and then execute our code the second time. That's the general idea anyway. So let's do something like, instead of this code that we have over here, let's print, no, wait a second. Well, we can print the relocating stuff, but first we need to check the value of the DL. So let's create a subroutine called relocation, and we will compare the DL register to 0x80, And if it's equal to that, we will jump to relocation. Otherwise, we will do the other stuff. But for now, let's just jump to halt. Otherwise. Or let's see. No, not to halt. Let's say we jump to successful or something. So our successful subroutine will we will want to move into AX, second message. We want to push it and we want to call print. And then we can jump to halt. Otherwise, we will do the actual relocation, starting by printing the message that we are relocating. And how are we going to do this? Well, we could do a loop, which basically just starts at the beginning here and manually copies each byte up to 512 bytes. But there is a better way. We can use a special instruction which is called rep move SB. What this does is it takes the memory address inside of the SI register, and this is the source. So it uses this as a source for the copy operation, and it uses DI as a destination. And inside of CX, we put the number of bytes we want to copy. And then we just do this instruction without any arguments. So let's move into DI. Or let's start with SI. So the destination should be 7800, as I mentioned before. And let's do the destination field as 7C00. So that is, let's see, no, the other way around. So we want to copy from 7C00. That's where this code is located. And we want to copy to the 7800. And then we do a rep move SB. And when we have done the copy operation, we will just jump into that code. But before we do that, we need to move into our DL. Some other value like 0x90, so we won't just repeat this over and over. And then we can do a long jump, and we do that by specifying 2 parts of the address, this and this. This is the right thing. So this basically means that we will do a jump to 0 as the segment, basically. And if we have a 0 segment, we will jump to this address, which is what we want to do. And let's and if this would fail somehow without crashing, we could end this by jumping to halt. So if this works, first we're going to see the relocating. Then we're going to copy everything to our new location. Then we're going to relaunch this whole program. with the only difference being where we store it in memory and the value of the DL register. And then we're going to print the relocation successful the second time around. All right, that's the idea anyway. Let's see if this compiles. We got a warning 72. Yeah, that's right. This should be a colon afterwards. All right, let's see if we have a boot.img. Yes, we do, and it's 512. Let's run it and see what happens. Relocating, and then nothing. That's a little bit disappointing. Right, so let's see here. This prints the first message, which means that this was equal to 0x80. Maybe if we execute the halt directly after the print, it might actually halt before it's able to print. So let's do the loop here, the endless loop, but let's not do the halt. And let's see if this makes a difference. Huh. Wait a second. I set the SI and the DI, but I never set the CX. We also need to set CX. And this should be 512, so I think that's 0x200, if I'm correct. Let's see. Let's do dec and 0x200. Yes, that's 512. All right, let's see if it works this time around. It's weird that it's only printing 2 of the dots, because I have 3 here in the first message. Destination 7800. Let's double check the syntax for rep move SB. Let's search for rep stars Felix. Then we come to this Felix Coutier page, which is often the best one. Right, so this one, I think, no, this one. So we move CX bytes from SI to DI. And we move 512 bytes. Wait a second. Now I see. Right. If we do an obj dump of the boot.img and we grep for 7c, obj dump. So look at this. This is where we call the string, the print function. So we specify the address hard-coded as 7c each time. And we can't do that because we are at 7800, right? So we need to be a little bit more clever. We need to have some kind of offset. So let's say we have a word which is 0 by default. So when we grab the address inside of the print, so let's see, we put it inside of SI. So what we want to do is we want to take that address minus the offset, which is 0 by default, which means the address will start with 7c. So let's start there. So let's see here. Let's move into BX, the offset, but if we use the offset address, it will still be the same problem. It's a little bit tricky. Well, we don't have to do an offset. We can use the DL here as well. So let's do something like this. Let's compare DL to 0x80. And if it's not equal, if it is equal, let's jump to no offset. Let's just do no off. Let's make it a local label. So let's say we have it here, no off. And then we're not going to do much else. But if we are in the second iteration, then we want to sub the SI by 0x400. I think this should be enough. Let's try it out. Okay, this time we got 3 dots. But I noticed we have only, how many calls do we have to the print? Or actually, that doesn't really matter. But I saw a lot of different 7Cs here. 57, 67. Let's do something like this. Move AX. Okay, so that's the stack. It doesn't hurt that the stack is 7C, actually. What about this? This is probably one of the prints. 7CO2. Yeah. What's this? Move SI 7C00. That's the actual relocation code. So that will not run the second time, so that shouldn't be a problem. What about this? 7C12. That's the second message, I guess. I think this should work. Let's see if we have this address. And we minus 0x400. Then we get the decimal value of this. And the hex value of that is 7812. So that should be the right thing. Maybe it's the actual print that fails. This thing should probably be after the call to print. Because otherwise the return address will fail. That's probably it. So let's see here. Where do we print stuff? Here is a call print. So afterwards we want to minus the stack pointer. And same here. Could it be so easy? There we go. Relocation successful. Ladies and gentlemen, we have successfully relocated. Nice. So now the only thing left is to run the code for the second iteration, which goes through the partition table and finds the first partition, which is bootable, reads from disk and boots from that. So we'll be right back after this. All right, you guys, welcome back. So before the break, we finally managed to get this relocation working. So now the next step is to parse the partition table. But first we need to have a partition table because this is just placeholders. So I'm thinking I'm gonna code a bash script which is in charge of that. So let's say we have a ptable.sh. So the use of this script is to take the partition table from the main hard disk drive and put it into our put it somewhere. So let's say we have the first sector, the first 512 bytes of the primary hard disk we have in a file called disk. So we want to check if that file exists. And if not, then we want to, let's see here. Then we want to print an error message. So something like disk not found, and then it tells to run the following command. So sudo dd, and the input file is the primary hard disk drive. Output file is our disk file. We want to have a sector size of 512 bytes, and we want to copy one sector. So this is what needs to be run before we execute the script. And if not, we get this error and we quit. Otherwise, we can start parsing this thing. So I'm going to use two temporary files, tmp1 and tmp2. So let's start by removing those if they already exist. And let's suppress any error messages. So let's see. So the disk file contains all of this, but we want to replace the code part with our own. And these parts we don't care about. So we can actually well, doesn't matter. However, this we want to keep, and we can take this as well because it makes things a little bit easier to take from here and until end of file. So this we want to keep in one file, this we want to keep in one file, and then we can assemble these into our binary, our boot.image. So let's see how we do this. We want to take the input file of our boot.img, and we want to create one of the temporary files. Maybe I should be more proper. And let's set the size in bytes to 1. And then we want to take, we can't specify hex values here, so we need to do it like this. So we want to take, let's see here, we want to take BE number of bytes. So let's put it inside of here. So this will copy the first thing. Secondly, we want to take the disk file as input, and output is going to be our second temporary file. We still want the byte size of 1. And now we want to skip BE bytes. So we'll say skip, and we do the same trick. Paste it inside of here. Let's do small letters. Not that it matters. So at this point, we have the entire new image in 2 files. So we just need to combine them. So we can simply do cat tmp1, tmp2, and we can concatenate it into, well, a new boot.img. This should work, I think. So let's try running it once. So what do we call it? ptable.sh. So now it should fail because we have not generated that disk. But then we can just copy this whole thing. Oh, should be dd space and if equals this. So let's try this again. Okay. So now we have this disk file. So this is the current master boot record, and we want to replace it with our code, but we want to keep the partition table. So now we can run our script. Okay, and we can check our boot.img. It's still 512. That's a good sign. And let's do an obj dump. Jump to 50 and down there. This looks like our code, right? And if we go down to the partition table down at BE. So here, starting with 80, we have the first partition table entry. So 1, 2, 3, 4, 5, 6, 7, 8 bytes. Looks right. So the interesting thing for us is this first field, which contains the bootable flag. This right here. Bit number 7 inside of this byte is the bootable flag. And then the next 3 bytes is the CHS address, which tells us where on the hard disk drive, physically, where the where the first partition's data is organized. All right, looks right. So let's integrate this into our build system. So when we create the boot.img, at the end here we want to set ptable.sh executable, because when we update that file using the method I'm using, we lose that flag. So let's put it in here. And then we just run this thing. And then we will have a new file with the correct partition table and our code. Easy peasy. Maybe at the end, by the way, we can remove those temporary files, like so. All right. So next step is going through the partition table, because even though we put our bogus stuff here, our end file will contain the right partition table. So we can write our code as if these values were the correct ones. So the first thing is iterating through these 4 partitions, looking for the bootable flag, and the first partition we find with the bootable flag set, that is the one we want to boot from. So this code right here, where we currently have this relocation successful, instead we want to print something like looks bootloader. And instead of jumping to halt at this point, we want to call some function for finding the right thing. I guess we could write a function called getCHS, which looks for the bootable flag, and if we find it, we read in the CHS values, the cylinder head sector from the hard disk drive. And we can say that we have an error if the carry flag is set. So afterwards we can have jump carry to error. And so this is basically if we don't find any partition. And we can move into AX message 3, let's say, or error message 1. Push AX, call print, and decrease this. And then we can jump to halt. Let's create this error 1. Maybe we need to clean up a little bit with those if we don't have enough room later on. But let's cross that bridge when we get there. No bootable partitions. Something like this. However, if we don't get this carry flag, we want to do something else. But let's create this get CHS function first. So let's put it up here. So get CHS. We wanna let's see. We wanna push BP and move into BPSP. As usual, and we don't take any arguments or parameters to this function. So let's see here. So we want to start at the first partition, which is called first. And if we look at this format here, we see that the first thing is the drive attributes, which means this is the thing we want to look at. So let's start by moving into, let's move into BX. The address of partition. We clear out AX, and then we move into AL, the address inside of BX. So now AL will contain our data, and BX will contain where the address of that data. Alright, so how do we get the 7th bit out of this? The easiest way is to do an AND operation. So we AND AL with something which looks like this. So this is bit 7. And this is 0x80, which we have seen before. So if we AND it with 0x80, we can just compare it to 0x80 afterwards. And if it is, then we know that this is set. And we should probably do this inside of a loop though. let's say this is a loop 1. So if it's equal to 80, then we can move to the next step. Let's call it, well, that's the actual CHS part, so let's call it that. So here somewhere we're gonna have that stuff. However, if this partition is not bootable, then we want to go to the next one. So we want to add on 2 BX. We also need to keep track of how many we have gone through. So let's move into CX number 4, I guess. So it starts as 4, then it becomes 3, 2, 1, 0. Okay, so we need to check it by the end. So we decrement CX, and if it goes to 0, in that case we want to jump to the error condition, because then we have gone through all the different ones without finding what we're looking for. So the error condition is just that we set the carry flag, and then we move into SP, BP, we pop BP back into place, and we return. However, if we are not by the end, in that case we want to add into BX 16, because it's 16 bytes to the next one. And then we want to continue looping, so we jump back up to the loop. So this is the code for finding the first partition with the bootable flag. And what do we do when we find that one? Then we can copy into AX the value of BX, which currently points towards the first thing in that partition. And then we want to go to the CHS. Maybe we don't need to do it this way. Let's just add on 2 BX the partition. Let's see how we do this. Partition dot start, I think we called it. So now BX points to that, and we want to read in 1 byte at a time. And put it in the right place. And where is that? Well, we want to execute an int 13h. So read disk sectors. This is the function in the BIOS we want to use to read in from the disk. So we want to put, as you can see here, we put in the drive number and the cylinder, the head, and the sector. So let's put it in those places. So first we start with the cylinder. So we move into, let's see where we're going to put that. So some stuff we set into AX, some in CX, and some in the D registers. So we need to clear out CX at least. So let's start with the cylinder, which we're going to put inside of CH. So we move byte into CH at position BX. Then we can increase BX, so we go to the next byte. So that's the head number, which we're going to put inside of DH. So we move byte DH, BX, and then we increase it again. And this time we want the sector number, which is inside of AL. No, number of sectors. We want this one, sector number, CL. And now we have everything that we need from here. So we can just move into SP, BP, we pop off BP and we return. And before we return, by the way, we can also clear the carry, since we use it to signal an error. All right, so something like this. So when we have gotten the CHS, we want to read in the first 512 bytes from that location. So let's call something like disk read. By the way, we need to do the error check first, then we can call disk read. And then we can check the error again. And how will this disk read work? Well, we already have most of its parameters already set up. So we'll just create a function like I've done before. So we push the BP, we move BP into SP. So we have the track, the cylinder number, we have the sector number, we have the head number. The drive number is already inside of DL, you remember, 0x80. So the only thing we need to set is the AX bytes, and we need to set BX to where we want to store this thing. So let's move into AX. Number of sectors is a low byte. So this is going to be 0x02 and then 1 sector. And bx, well, where do we want to put this stuff? Inside of FC00. So that's the whole point why we messed with the relocation. So we can move, 7C00. So we can put it right here. And now we just do int 0x13. And the carry flag is 1 with an error, so that suits us perfectly. So let's clear the carry before we do this. And then we can simply return from the function. So move SPBP, pop BP, return. Okay. And when we have done all of this, the only thing left is to execute that code. So inside of the main function, the only thing left is to, is to jump to the address of 0, segment is 0, and the address is 7C00. And then if we fail, we can jump to halt. And that's it. After the break, we're gonna check if this code works. See you in a bit. Sup guys, welcome back. So before the break, we basically finished the whole thing. I'm just gonna take a moment to fix some error that I noticed. So let's see our function for get CHS. I call this loop 1 and I jump to loop here, so let's change this to loop. And one other thing I want to add, so when we boot, I want the user to press enter so we can see a little bit more what's going on. Otherwise it would only happen instantly. So let's change this to looks bootloader. Press enter to boot Linux. Maybe I should have prompt like this. Yeah. And how do we read from the keyboard? There should be some BIOS interrupt for that. Let's see how we get back to the main page. So BIOS keyboard services. This one is good. Wait for key press and read character. So the only thing we need to do is set age to 0 and call interrupt 16. Then it's gonna wait for a key press. And I guess any key press. So let's change enter to press any key. So let's see, where do we print message to? I guess it's inside of main somewhere. Here. So get CHS. So at this point we have done the relocation, but we haven't actually found any partition with a bootable flag. So I think it's a better way to put it here, actually. Yeah. So let's just add, let's clear out AX and call int 16. No, not 16. Hex 16. But maybe not, because this get CHS function, it prints this error. If it fails, so in that case this error will be printed and then waiting for a keystroke, and that's not what we want. So I guess we can move this here. Yeah, that's gonna be good enough. Alright, something like this. Let's see if it compiles, and let's see if it fits. We only have 440 bytes for the code. Discrete not defined. Oh, we never did discrete, did we? Or maybe, no, wait, discrete. I think we did it, right? Discutil, why did I call it discutil? Discrete, of course. Of course. Huh. It compiled without any error, and it fit. That's pretty remarkable now. Let's do an obj dump and see how much code there is. So we go all the way to 12D, and if we take the decimal of 12D, 301. We could actually add at least another 100 bytes. But okay, that's pretty nice. How do we test this thing? Maybe we can test it, at least the part of it, by running make run. Press any key to boot Linux. No bootable partitions. Well, that makes sense because we are running it in a virtual machine, right? And that virtual machine does only have this boot sector. It only has 512 bytes on the actual hard disk drive. So in order to test this properly, we need to install a real Linux server, at least a fully equipped and installed virtual machine, and then we can run this thing on that virtual machine. But I think this is good enough for today. I really hope you liked this episode. It is one of the most advanced and low-level episodes I've done. And if you want more like this, make sure to like and subscribe and maybe even hype, who knows. And we will finish this bootloader in the next episode. So thank you for watching. Thanks for today.